Hey guys, one of the most important tools that we're going to use when dealing with forces is something called a free body diagram or a force diagram. These are really common. In fact, on the AP exam, you're almost guaranteed to see at least one, possibly more, at different points on the exam. And when you see this is a chance to be like, yeah, I got a free body diagram. They're like free points. When you have to draw your own, they're usually worth 2, 3, 4 points. So it's a great opportunity to get some points there on the exam. All right, so I'm going to introduce them to you today. Now, the first thing that you need to understand is that when we're drawing a free body diagram, everything is a box. All right, if I draw a box and I'm going to do a free body diagram on it, then I will draw my box like this. All right, if I decide that I'm going to do a free body diagram on an apple, then I will draw it like this. If I decide that I'm going to do a free body diagram on a Tyrannosaurus Rex eating a chicken, it will look like this. All right, so each of those, every time you're just going to put a box. The individual pieces are less important. Sometimes it's helpful to have a drawing off on the side so that we can see what it's touching and how it's different things that are happening there. All right, and so we will use that, but as far as the forces for now, a free body diagram can just be drawn just like this. Draw a box for whatever your object is. All right, so what we're going to do is I'm going to show you a couple of examples. We're going to talk about the forces. You've already been introduced to different types of forces, so we're going to look at what that might look like. All right, so first thing, let's just take a simple situation where we have a desk and we have a book that is sitting on the desk. So in a free body diagram, what we want to show is all the forces that are acting on our object. And the hope is that we can see whether the forces are balanced or whether there's an imbalance or something like that. Various things that we'll look for this as you'll get used to as we go forward. Today, just get used to the idea of how do we draw a free body diagram and what are some of the different parts of that. All right? So first, I've got a book. I'm doing a free body diagram for the book right now. So the book is sitting on the table. The table, of course, is just on the ground. Now, what are the forces that are actually acting on my book? Now, you might say, well, gravity's pulling down on it. Yeah, all right. So we're going to draw the force of gravity. The force of gravity is downwards. So I'm going to draw it with a downwards arrow. The force of gravity is a vector. And so we draw that vector by showing the arrow. Remember, a vector has magnitude, which is shown by the length of my arrow, and it has direction, which is downward. Now, what other forces are acting on my book when it's sitting on the table? Hopefully you're saying, well, Mr. Bowater, the table's touching the book. Yes, you are correct. Crazy person in the back. There is the force of the table. Now, that is a normal force. Okay? Now, I in this class will always label it as Fn, normal force, of the table. If you just want to put force table, that's acceptable as well. But I will always label normal forces with the N just to remind me that I'm talking about the normal force of the table, not the frictional force or anything else that might be associated with that. Now, what you might notice is that the object is at rest. In order for the object to be at rest, all of the forces have to add up to zero. They have to balance out. It has to be in what we call equilibrium. Equilibrium is what happens when all of the forces added on an object cancel each other out. And so in order for the book to stay at rest on the table, all of the forces on it have to balance out. Now, these are the only two forces. Okay? Now, some of you are thinking, yeah, but the table's the floor is touching the table, which is touching, that's fine. That's lovely. You can do that later. But right now, the floor is not touching the book. Therefore, the floor cannot exert a force on the book, period. The only things that can exert a force are the added distance forces that we know of for right now, gravity, and then also contact forces, okay? Like the normal force, like tension, like friction, things like that. So my free body diagram here will look just like this. The only thing I want to say is, remember, it does need to be balanced in equilibrium for it to stay at rest. So these two should be the same length. If you're one of those people that's like me that just can't ever really get it the same length, what you need to do is like what you learned in geometry class, is put the little hash mark there saying, you know what, these two are the same. Even if they don't look the same, I'm really trying to make them the same. So I'm putting the hash mark there. Now it's clear. Those two need to be the same. All right? So let's do another one. Let's do a free body diagram. So the same situation, book sitting on the table, sitting on the floor. Let's do a free body diagram for the table. All right, so we got the table. All right, now what are the forces acting on the table? Now the one everybody always says, I know, gravity. Yep, very good. Gravity is acting on the table. Now, if you think about it, the gravity on the table is probably going to be greater than the force of gravity on the book. So I'm going to make that a little bit longer. Anytime you put things next to each other, force-free body diagrams that are close, it's helpful to make sure that you demonstrate which ones are bigger, which ones are smaller. So this is the force of gravity on the table. And if you want, now that I've got two FGs, I can label this as force of gravity on the table, just like that. And what else? What else is acting on the table? Well, the book. Obviously, the book is sitting on top of the table. What direction is the book pushing? Well, because gravity is pulling down on the book is pushing downward on the table. Now, you may notice this for those of you that know Newton's third law. You may recognize that if the table is exerting a normal force up on the book is exerting a normal force down on the table. So, therefore, we've got that the book, about the same force as this, should there be a normal force of the book pushing down on my table. All right? Now, I got that. So the book is touching it. The floor is also touching the table. So I got to include that force as well. Now, the floor, of course, is pushing upwards. And so I'm going to include the force of the floor going upwards. Notice that there's nothing else touching my table. So therefore, there won't be any other forces. In order for the table to be at rest, the forces are going to need to be balanced here. And so if I look at how big that is and how big this is, I'm going to put those together, and the force right here, that'll be the normal force of the floor, which should be the same length as both of these added together. All right? And I may look at that and I may say, well, you know, that actually looks like kind of the same as this, so I'm just going to make this a little bit shorter. I know, you can't do that. Well, you can. You could just erase it, make it a little bit shorter. But as long as it looks right, it's going to be fine. Okay? They're not going to pull out a ruler and be like, you're half a millimeter off. But if they look at it and it looks like it's a little bit different or looks like it's off, then they can go ahead and take off. Most of the time, they won't be too crazy about that, but you should do your best to make sure that you are representing the forces as vectors, which means both the direction and the magnitude, the length, are important here. All right? So there we go. We've got the forces on the book. We've got the forces on the table. All right, let's look at another one. Here, let's get rid of this. Actually, we can just work here. Let's say that we've got a student that is falling with a parachute. Now, this is the person in the parachute. All right, so you've got this person here, just like this, and they're connected to a parachute here. All right? So sometimes the drawing is helpful, but I'm not going to do my free body diagram here. I'm doing the free body diagram on the person. All right? So if I've got the person here, what are the forces on the person? Well, of course, you got gravity. Yeah, I know. We got gravity there. So I'm going to draw the force of gravity on the person. Okay? What else is acting on the person? Now, hopefully you're thinking about, well, what is touching the person? Well, you've got these strings on the parachute that are going to be pulling up on the person. Now, because it's strings, we're likely to call that tension. All right? So we'll have the tension of the parachute, but tension of the strings. All right? Now, if you had to, you could create a different tension force for each of those strings. But right now, we'll just kind of all say, okay, well, there's tension pulling up on the person. All right? Now, we can think through, are there any other forces, right? You may be thinking, well, maybe there's some air resistance. All right, if we want to include air resistance, we'll include just a little bit of air resistance. Just make sure that if you decide to include air resistance, what you're thinking about is the air resistance on the person, not the air resistance on the parachute, right? It's tempting to say, well, the air is pushing the parachute up, there's drag there, therefore the person's slowing. That's not on the person. You only want to include forces on the object, this object right here, which is the person. So what's pulling on the person? You got gravity pulling him down, you've got the strings pulling him up, and then you've got possibly, as he's falling, a little bit of air resistance here. Now, if he's got the parachute out, there's a pretty good chance that he's falling now with a constant speed. He's not speeding up anymore. That's the whole point of the parachute, which means that these should add up to be the same as my force downwards. All right? Awesome. So, let's look at another one. Let's look at, how about this one? So I've got a ramp, and then, sorry, I should draw my picture down here. Got a ramp, and we've got a block that is sitting on the ramp. What are the forces acting on the block? All right, what do you got? What do you got? Well, hopefully you got first that we've got the force of gravity, right? Now, the force of gravity always just acts straight down. So we've got the force of gravity pulling straight down on it. Okay? Then what? Then you've got it's touching the ramp, right? So the ramp is going to exert a normal force on it. But that force has to be normal. Remember, the whole point of normal force is not that it's ordinary or common. It's the fact that normal means perpendicular. So if the surface is this direction, then perpendicular is up in that direction. And so when I draw the normal force of the ramp, it needs to be perpendicular to the surface. So it needs to be kind of up in this direction. So this right here will be the normal force of the ramp up in that direction. Now, what you might notice is that if these are the only two forces, will it be balanced? Will those forces cancel out? And hopefully you're going to say, well, no, even in the best scenario, if this is vertical, I might be able to balance the vertical part, but there's going to be some more of this force over here that is not balanced. So in order for this block to stay at rest on the ramp, there needs to be another force. What could that be? Well, hopefully you're thinking, I know, it's friction. Yes, friction, right? The block, if there was no friction, the block would slide down the ramp, right? It would move kind of in this direction in general. The fact that it's not sliding down the ramp means that there must be friction that is opposing that. And we'll spend a whole day, maybe even two, on friction later, so we'll get more details. But right now, what you need to understand is that friction always works parallel to the surface, which is different from the normal force. The normal force is always perpendicular. Friction is always parallel to the surface, and it always opposes motion, or opposes an attempt at motion. So the block's trying to slide down the ramp, and friction's saying, nah, you ain't going anywhere, you're staying right here. And so therefore, friction should be up the ramp, kind of in that direction. Otherwise, it would slide down. So now I'm going to add in the force of friction, just like that. And you might be able to then kind of reason out, okay, so I've got a little bit of horizontal here, a little bit of horizontal there. I've got some verticals. Those verticals might balance with this vertical. And so therefore, it kind of makes sense that we could figure out that this ends up balancing in some way. That's a lot better than it was before without the friction, when it was very clearly not balanced. It would not have been in equilibrium. All right? All right, so we've got 4 examples right now. I'm going to go ahead and erase these, and we'll look at a couple more examples, maybe 3 or 4 more, and then we'll be done with this video. All right? So hang on just a second. All right, so we've done a couple of different things. Let's see if we can mix things up a little bit, make it a little bit more challenging perhaps. All right, let's look at a ball hanging on a string. Let's start with a simple one, right? Just a simple first, all right? So we got a ball hanging on a string. What are the forces acting on the ball? And I know I did a lowercase a and everything else is all caps. I don't really care. I'm not in English class. I can capitalize whatever I want. All right? So we've got the ball. What are the forces acting on the ball? Well, we got gravity. Okay, so we got force of gravity down. And then we've got tension, pulling up, right? And because the ball is at rest, it's in equilibrium, we know that that force must be equal to the force of gravity downwards. Pretty straightforward, right? Now, let's look at a couple of different situations with this. What would need to happen in order to allow the ball, so now we've got the same situation, but now we have a ball hanging by a string that we want it to accelerate upwards, okay? If these two forces are equal, then it just continues doing whatever it's doing. And so for this to happen, in order for it to accelerate upwards, what needs to be true? Well, hopefully you're recognizing that, well, in order for that to be true, they can't be balanced. Because if they're balanced, it ain't accelerating. So therefore, I need my tension to be greater than the force of gravity. Now, the force of gravity didn't change. That's the same as it was before. But what's different is my tension is now bigger than it was before. And if you don't like how long that is, you can make it a little bit longer. If my tension is bigger than it was before, then I have more force up than I have down, and so therefore it will accelerate upwards. Okay, now accelerate upwards could mean a whole bunch of different things, but it does mean that the acceleration is in the upward direction if this force is bigger than that one. Now, what would it need to look like in order for the acceleration to be downwards? All right, hopefully you're thinking about that. You're going through the ideas. You're saying, well, I'm not adding any more forces, right? So I still got the ball. I still got the force of gravity, which has got to be the same as it is before. Force of gravity ain't changing, y'all. Okay? So that force is the same. So what can I change? I would have to decrease the tension, right? By having a smaller tension, something like this, the force downward would be bigger than the force upwards, and then it could accelerate downwards. Now, there's a number of different ways I could do this, but one is if I start at rest and I start moving it downwards like that, that would make the tension in the string a little bit less. All right? If I'm moving upwards, then I just start moving upwards a little bit less quickly, and again, that would mean the tension's a little bit less than it was before. That'll allow me to balance it out, to get to this situation where tension is less than the force of gravity. All right? Now, so we've got this situation where it's at rest. We've got this situation where in order to accelerate upwards, that means changing velocity, accelerating upwards, tension needs to be bigger. We got this one where the acceleration is downwards, negative, and so the tension has to be smaller. What would it need to look like in order for me to move upwards at a constant speed? Go ahead and think about that. If you need to, pause the video. But what would it need to look like in order for me to move upwards with a constant speed? Not accelerating upwards and not accelerating downwards. What would it have to look like to be able to move up at a constant speed? Hopefully, you got something that looks like this. Hopefully it looks familiar. It looks just like this one, right? In order for it to move upward at a constant speed, in order for it not to accelerate, the forces must be balanced. If it's already moving upwards, in order to continue moving upwards at a constant speed, you just make sure that those two forces are equal. And if those two forces are equal, it will not accelerate. And by not accelerating, that means the velocity will stay constant. The speed will stay constant. Think about that a little bit. We'll talk about it a little bit more in class, but that's kind of the basic idea there. All right? I got one more that I'd like for us to look at. This one's a little bit more complex, so give me just a second to set it up, and this will be our last example for today, all right? So, here we go. All right, you ready? This is our last one. What we've got here is we've got a ladder that's leaning up against the wall. All right? What are the forces acting on? Can we create a free body diagram for this ladder that is leaning up against the wall? All right? So hopefully you got the force of gravity. Good job, you got one. All right, so we got the force of gravity pulling down. All right, I'm not going to worry about the length because I don't have anything else to compare it to right now. So force of gravity. What else do we know has to be there? Okay, think about those contact forces. What is touching the ladder? Well, you see right here at the ground that the ground is touching the ladder. The ground is flat horizontal, so therefore a normal force of the ground would be pushing up on the ladder. Okay, so we've got the ladder, the normal force of the ground, just like that. Okay, is pushing up. I'm not going to worry about the length yet. I can always change those later if I need to. All right, so then we've got this wall over here, right? This wall over here is vertical, so what direction can it exert a normal force? Well, it can exert a normal force in this direction, to the left, right? So I'm going to have a normal force, still a normal force, of the wall to the left because it can push perpendicular to it. Now, when you look at these forces, are they balanced? Is there any possible way in our minds that these can be balanced? Hopefully you're saying, no, that's wrong because I got a force to the left and I don't got a force to the right. That means my ladder is going to go whoop. You don't have to say exactly like that, but something along those lines. You should recognize that it's not exactly equal. So what needs to happen? Well, I definitely need a force going that way. So where is it? What could it be? Is anything else touching it? I don't see anything else touching my ladder. Oh no, I just broke physics! No, we didn't break physics. It's fine. They were just missing something. What are we missing? What are we missing? Well, what would happen if you stood on this ladder and there was no friction? Usually the best way to think about friction is to say, well, what would happen if there was no friction? Well, in your mind, you should be able to think about, well, if I stood on this and there was no friction, the ladder would go rip, and it would just slide right down the wall. Okay? Now, what that means is that this should be sliding down, and this should be sliding out this way. So remember, friction tries to oppose motion, or tries to oppose an attempt at motion, which means if the ladder would be moving this way, that friction will oppose that motion and go to the right. So we got the friction with the ground, which is going to be parallel to the ground to the right. So we're going to have friction with the ground going to the right. All right? And that then has to be the force, and I know they don't look the same, but I just marked them. They are the same. You can see right there. So those two have to be the same. Whatever force the wall is exerting this way, friction's got to do exactly the same force in the opposite direction. What we will also see is this, is that, well, if the ladder should be sliding down, then it is very likely that there's also some friction that's going to be pushing up as the ladder tries to slide down the wall. So that friction up, we're going to add in here as well. So we're going to have the friction of the wall there, which means the normal force of the ground will not be equal to the force of gravity, right? Those two can't be equal because there's another upward force there. Now, the strength of that will depend on how much friction there is. More friction means that there's less force of the ground on the ladder. But now what we've done is we've included every single force that has to be there, and we've given it the capability of balancing horizontally and balancing vertically. All right? So I hope that's been helpful in introducing you to free body diagrams, in thinking about what we're trying to show, and in thinking about what we're trying to accomplish with them, and what we hope to see, and how we can kind of analyze it at the end and say, am I missing something, or do I got everything there? All right? So I hope that's helpful, and I'll see you next time.